Good morning, math peeps. Before we start today's lesson, I would like you to try a review problem from yesterday. So here it is. Hit pause and see if you can do this on your own. If you were in class, that's what you would be doing for bell work. So I want you to check whether or not you can do this on your own, and then I'll show you how it's done and work it out for you when you're finished. Okay, so anytime I see these two symbols together right next to each other, I think flip, flip. I know that that's informal. That's okay. It's what works for me. For me, I'm going to use the flip, flip. If you'd rather use the formula that I gave you and you understand how to use it, then you can do that too. So I'm going to use the flip, flip, and every time I do that, I pretty much always, I train myself like the dog that I am. I train myself, I'm going to write the original function and the inverse function, and I always do it the same. That training my mind to always do the same thing helps me predict where I'm going. Okay, so this question, you have to recognize that that's an inverse, and this is an x-coordinate, because it's always f of x, but that's the x-coordinate on the inverse. So that tells me this x-coordinate. And I know because of this symbol that what they really want is the slope there. And this is the question I'm trying to answer. Based on yesterday's lesson, though, if this is my x-coordinate on the inverse, then it's really the y-coordinate on the original. I need to now find the x-coordinate here and the slope there, but that won't be the answer. I'll have to flip it to get the slope of the inverse. So that's my goal. All right, so this is the y-coordinate of the original function, but I need the x-coordinate that goes with it. So if y is 2, that means this is 2, and I need to find the x-coordinate that goes with it. Okay, so y is 2. Find the x-coordinate by solving this. Add 3 to both sides. Divide by 5, and you can see that x would have to be 1. Now that I know what the missing piece is right here, okay, now I need to find the slope at 1 on my original function. So if I need the slope at 1, then I'm going to find the derivative at 1. So first, just find that derivative, which is easy, 15x squared. Now find the derivative at 1 so that I have the slope. Plugging in 1, I get 15. So I now know the slope here is 15, but that's not the answer to my question because for the inverse slope, I have to now flip it. The answer to this question would be 1/15. Hope you got that. If not, let me know, you e-learners, because I can come up with a few more problems for you to practice, okay? All right, moving on to today's lesson. Today's lesson is motion of a particle or an animal or a turtle or whatever, motion along a line. And if you're in physics, then you've gotten a lot of this too. Let's start with just a conceptual beginning. Oops, never mind, didn't know where I was going. First, we'll start with some notation, okay? This is something that the AP people love. There will be a lot of questions about motion of particles and turtles and things, okay? This is a huge concept. Big, 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 big. And by the way, I made a page for notes that matches this PowerPoint. I highly recommend you print out that page. It'll save you time and allow you to follow along a little bit better. So this is in the notes. If you want to print it out, hit pause and do that now. All right, if position is given, like feet, where you are located to original position, okay? If position is given, and by the way, sometimes they'll use P of t, sometimes F of t, sometimes it'll be S of t, which is, I think, what we're going to use today. If the original equation stands for position, where are you after so much time, then the derivative of that, we did this earlier in the year. Let's say this was feet, position given in feet. Then velocity would be how fast you're going. That unit might be feet per second. Okay, and that's the rate of change of the position. So that's the derivative, okay? So velocity is the derivative of position. And any one of these three symbols for position, there's no standard notation for position, but there is standard notation for velocity and acceleration. So if position is given, The first derivative represents velocity. The second derivative, the derivative of that, would be the rate of change of velocity. How fast is my velocity changing? That's acceleration. And the units for that would be feet per second squared. Again, assuming it's feet and seconds to begin with. Lastly, speed. Speed is the absolute value of velocity. So velocity, if I have a positive velocity, it tells me how fast I'm going, and it tells me what direction I'm going. Positive would be to the right, negative to the left, unless it's an up-down situation. But speed is the absolute value. Speed is always positive. So whether I'm going backward or forward, speed is always positive. I think it'll be a little bit clearer once I give you an example. All right, let's start with just a conceptual idea. Let's say this is a particle. This is the graph of a particle moving along the x-axis. It's always along a straight line. It could be the y-axis up and down. This is given to be a velocity graph. Make sure you always pay attention to the title of the graph. Take them a moment to consider that, okay? So this is the velocity of the particle or the turtle or the whatever the case is. All right. Well, if velocity is positive, that means the particle is moving to the right. If velocity is negative, the particle is moving to the left. So in this problem, all my negative velocities are down here. All of that represents particle moving left. Okay? All of my positive velocities, all of this, that represents particle moving to the right. So negative means moving left, positive means moving right. Okay? So, therefore, when is the particle stopped? Stopped, not moving. That means velocity is 0. The particle would be stopped here when it started, here, and here. Okay? When would the particle change directions? Well, if it's going left here and right here, then it changed directions here. Okay, so when the particle changes directions, it's going right and then left, or left and then right. It actually has to have a velocity of 0 in between. Okay, last let's talk about speed. Okay, let me erase all this stuff. Speed is the absolute value of velocity. Okay, so the speed right here is 4. The speed here would be 2 meters per second. Same as the velocity. Okay, but the speed here, that's a velocity of -2. That means it's a speed of 2. So let's try to describe what this particle is doing, or turtle, or whatever it is, okay? From here to here, the speed goes from 0 to 2. Speed, not velocity. Speed goes from 0 to 2. So during this point, the particle is speeding up. Here it's a constant speed of 2. Then we go from 2 to 0. So the particle is slowing down. Okay, all of that, the particle's going to the left, but speeding up because we went from 0 to 2, constant, and slowing down. All right, now let's look at the part where the particle's moving to the right. At this spot, the particle changes directions, and now the particle's going to the right for all of this. Well, now from here to here, we go from a speed of 0 to 4, so speeding up, constant speed of 4, and slowing down, going from a speed of 4 to a speed of 0. So, if speed is the absolute value of velocity, then think of it like this. As you go away from 0, you're speeding up. Speeding up is this spot and this spot, going away from 0, because speed is the absolute value of velocity. Slowing down would be going towards 0. This is slowing down, but this is also slowing down. Okay? So now we're going to make it a little bit more formal. Oh, before I do that, let me show you another option with speed, another way to think of it. Right now we're just kind of going informal. If speed is the absolute value of velocity, then you could take this entire graph and change it to a speed graph by taking anything that's negative, when you do the absolute value of it, it flips it and makes it positive. So this piece of the graph turns into something more like this. And now you can see speeding up, constant speed, slowing down. Speeding up, constant speed, slowing down. That's another way to look at it. Okay, put it all together with some formalities. All right, all of this, sadly, sorry guys, all of this is going to have to be memorized, okay? They love asking you about the direction stupid particles are moving. So memorize it now. Notice that all of these justifications, and you have to write these justifications every year on the AP exam, okay? If they ask you, is the particle moving left or right, the first thing you write is this justification, okay? Notice that all of these justifications require velocity. So if they give you position, your first job is to get velocity, get the derivative, okay? As soon as they say particle moving left, you write velocity negative. If they say particle moving right, you write velocity positive. If they say particle is stopped, velocity is 0. Okay, particle changes directions. That means it either went from left to right or from right to left. So it either changed from negative to positive or the other way around. So what you need to say for this is velocity changes sign. You have to say velocity changes sign. That also implies that velocity is 0, but you don't actually have to say that, but it wouldn't hurt you. Okay? So particle changes directions, velocity changes sign. Okay, all of this has to be memorized cold. All right, speed is the absolute value of velocity. Now, I showed you how to handle that graphically, but write this down for now, though I haven't mentioned it yet. Here's the formal way to justify it if I don't give you the graph and instead I give you an equation, okay? All right, so I haven't shown you what this means yet, but since all of these require comparing velocity to 0, we're comparing whether it's positive or negative, we're going to use a sign chart. Now, this is the first day you're seeing this, but this will be something we do all year. Believe it or not, this might seem like a lot right now, but we will do this so often, it will be second nature to you soon. All right, so let me give you an example of how this works. Let's do it graphically again first. If this is a particle, if this is the velocity of a particle moving along the x-axis, then describe the motion of the particle. Start off informal. All right. Well, when velocity is positive, the particle's moving to the right. So velocity positive, particle moving right, that would be this and this. Okay, how do you say that? Moving right, if I had to. I'm not really worried about the real formal stuff yet, but the particle's moving to the right from 0 to 2 seconds, and then again from 6 to what appears to be infinity. That's particle moving to the right, okay? Moving to the left is where velocity is negative, all of that. When does the particle turn around? Velocity changes sign. That's 2 places, at 2 and at 6. When is the particle stopped? Velocity is 0. This place that we already said, this place we already said, and at the beginning of the problem. All right, now let's do speeding up and slowing down. Okay, speeding up. Think going away from 0. Speed is the absolute value of velocity, so ignore these negatives. Think of them as positives now. Okay, speeding up would be going away from 0. Here is speeding up, but this is also speeding up because you're going from a speed of 0 to a speed of 17. Okay, so we have speeding up is here, speeding up is here, and speeding up going away from 0, this would also be speeding up. Okay, speeding up going away from 0. Slowing down, obviously, it's everything else. So slowing down would be going from a speed of 5 to a speed of 0. That's slowing down. Going from a speed of 15 to a speed of 0. That's slowing down. Okay? Think going away from 0, speeding up. Going towards 0, slowing down. All right. Now let's do this algebraically. Okay. This is a very, very, very common type of question. You'll get it more than once on the AP exam, okay? And it can get more difficult, but you'll be ready for it when we get there. Here we go. When does the particle change directions? Again, first, make sure that you have a velocity. If the velocity equation isn't given, you have to first find that. If I give you position, do the derivative to get velocity, then answer these questions. Okay, part A. When does the particle change directions? When velocity changes sign. Okay, so how am I going to figure that out? When does velocity change sign? Well, if it's a graphing calculator question, I could graph it. But we're going to use what's called a sign chart, okay? First, find whenever we're looking for when velocity is positive or negative or when velocity changes sign, all of those require a sign chart. Here's how that works. First, find not when velocity is positive or negative. First, find when does velocity equal 0. Because then I can figure out when it's positive and negative. Okay, so set it equal to 0, factor, and we get two places where the velocity is 0. Now I'm going to make a velocity sign chart. Make sure you put the name. This is a velocity sign chart because we're going to use sign charts in this class for lots of things. On my sign chart, I'm going to put the two places where velocity was 0, 2, and 3. Now I'm basically going to check the sign of each of these regions and see in between them whether the velocity is positive or negative. Okay, so to the left of 2, this region, pick any number left of 2, such as 0, and plug it into the factored form. If I plug in t of 0 here and here, then I get -3 times a -2. A negative times a negative is a positive. For any number to the left of 2, if I plug it into this equation or the factored version of that equation, you'll get a positive result. Now, when you do this, you're not paying attention to the exact answer. You're just trying to figure out, does your velocity, because remember, this actually represents velocity, okay? We just factored it, but it's the same as the original equation. This is my velocity equation. We're just trying to figure out if we get a positive or a negative value. So now I'm going to skip over to this side, plug in a number greater than 3. Anything you want, 4, 5, 6, 1,000, who cares? If I plug in a t greater than 3, like 4, here, if I plug in a 4 here and here, 4 minus 3, that'll be a positive. 4 minus 2, that's a positive. And when I multiply two positives, you're going to get a positive. Okay? Now we've got to plug in a number between 2 and 3. Okay, so between 2 and 3, you might think plugging in a 2.5 or something like that is difficult. But again, we're not looking for the answer. We're looking for, do you get positive or negative? So if I plug in a 2.5 to this factor, 2.5 minus 3, that would be a negative. Plugging in a 2.5 to this factor, you'd get a positive, and a negative times a positive is a negative. Okay, so now we have our sign chart. We're going to use it to answer a bunch of these questions, okay? So, to answer part A, when does the particle change directions? That's when velocity changes signs. So that'll be when velocity goes from positive to negative, which is here, and when velocity goes from negative to positive, which is here. So the answer to part A would be when t equals 2 and when t equals 3. Okay? Part B, when is the particle moving to the right? Well, that's when velocity is positive. So that would be here and here. There is a slight glitch though. When we write that down, you might think, okay, the answer to part B would be this arrow is negative infinity to 2. We don't include the 2 because that's where velocity is 0, not negative. And we might think from 3 to positive infinity. And that's a really good guess. There's just a tiny little glitch with common sense. When is the particle moving to the left? If you say negative infinity, when this represents time, that doesn't make much sense because time cannot be negative. So you actually need to chop this graph off at 0, okay? So, because you can't have a negative time. So instead of negative infinity to 2, you should say 0 to 2. And we can put a bracket on the 0 because it's actually negative past that if negative time actually existed. All right, so my answer to part B would be this. Okay, part C. Well, hold on. Before I do part C, let's talk about some of the other stuff. If I said particle moving right, it would be the blue arrows. Particle moving left, if I had asked that, would have been here where velocity is negative. Okay? All right, now we're going to do when is acceleration positive? Well, this is velocity. It doesn't tell me acceleration. So now I got to go find acceleration. Okay? So if this is my velocity equation, now I need to find my acceleration equation. Well, acceleration is the derivative of velocity, so that's easy, 2t minus 5. Okay? Now, when is acceleration positive? If they say positive or negative, that's a sign chart. Okay? So acceleration is positive. I'm going to need an acceleration sign chart. Okay? I've got to make that a little neater though. Hold on. So now I'm pretty much going to do the process again, but I'm going to make an acceleration sign chart. Well, before you can start your sign chart, you have to find where does acceleration equal 0. Okay, because remember, these guys are where that thing is 0. So add 5, divide by 2, and you get t equals 5/2, or 2.5. Now, put that graph right above your velocity sign chart. 2.5 would be here. Okay. And now we're looking for the values around it. Well, if I plug in something to the left of 2.5, like 2, then my acceleration is negative. If I plug in something to the right of 2.5, like a 3, plug in a 3 right here, then your acceleration is positive. So to answer part C, when is acceleration positive? That would be from here to here. Okay, so the answer to part C would be from 2.5 to infinity. And again, don't include this point because that's where it's 0, not positive. So it's be 2.5 to infinity. That's my answer to part C. All right, last thing, part D. When is the particle speeding up? Okay, I'm going to show you the math on this, and then I'm going to show you why in a minute. If you go back to your notes, speeding up is when velocity and acceleration have the same sign. Slowing down is when they have opposite signs. Okay? Speeding up is when they have the same sign. Slowing down, they have opposite signs. So this is why you want to put your velocity sign chart and your acceleration sign chart right on top of each other. Okay, you kind of want to visualize them merging, okay, right here. So make separate sections. Before 2, okay, everything before 2, from 0 to 2, velocity was positive, but acceleration is negative there. Okay, before 2. So since there you have a positive and a negative, that's opposite signs. That would be slowing down. Next, between 2 and 2.5, 2 to 2.5, here velocity is positive and, oops, I don't think that is positive. I think I went through it. Hold on, that wasn't. That was a velocity that was negative. I just accidentally made that look like it. Okay. During that section, between 2 and 2.5, my velocity was negative and my acceleration is negative. Same sign means speeding up. So that's one of my answers, from 2 to 2.5. Okay. Now between 2.5 and 3, the velocity is negative there, but my acceleration is positive there. So negative, positive, opposite signs, that's slowing down. Okay, the final section, after 3, this is positive and this is positive, same signs, so that would be speeding up. So from 3 to infinity. Okay, so you got to basically take your sign chart, the velocity and the acceleration, and put one on top of the other and compare the signs, okay? Now, why is that our answer? If you know that this is a parabola, let me show you what that graph looks like. So remember, we already found when this equaled 0. So if we were to have graphed it, it's a positive parabola. that crosses the x-axis at 2 and 3. So this graph would go like this. I mean, I might not have it perfect. It's kind of actually horrible. But this was my graph of velocity. So if we answer those questions graphically, where we're talking about part D, speeding up is when you're going away from 0. So speeding up is away from 0. That would be from here to here. Okay? And from here to here. Same answers that we got with our sign chart. Okay, so let's go back to the justifications that hopefully you wrote down. Okay, let's study those one more time. Okay, all of your justifications require velocity. Particle moving left, Particle moving left, velocity negative. Particle moving right, velocity positive. Okay, those would both be done with a velocity sign chart. Okay? Particle changing directions. That means the sign changes from positive to negative or negative to positive. So that would also be a velocity sign chart. Okay? Speeding up and slowing down. Those also involve signs. Okay? For those questions, you find both velocity and acceleration. Put the two sign charts one on top of each other. Okay? If they have the same sign, you're speeding up. Opposite signs are slowing down. All right, this might be a little tricky, but you'll get used to it, I promise you. Your assignment today is a worksheet, and please be honest about the problems I need to work out for you, okay? Good luck, guys.